So we've learned about tensors, and we've learned that they transform in a particular way, and that's one of the ways you can tell that a set of coefficients is in fact a tensor. We've also learned lots of ways of creating tensors out of other tensors. We can add them, out of product, permute indices, do inner product, and so forth. They're basically just generalizations of scalars and vectors. And we weren't happy with just scalars and vectors because we wanted to go on to electromagnetism. And we noticed from an example that as we change reference frames, electromagnetic fields seem to turn from one to the other. And so we were looking for a higher dimensional object that contains both the electromagnetic fields, and it's just the coefficients that are changing as we change between reference frames. In other words, we're looking for a tensor. But unfortunately, the electric field is not simply a vector, just as the magnetic field is not simply a vector. They're actually a vector for each point in space. And an object for each point in space is called a field. And so we're really interested in tensor fields. Now we've already met scalar fields. A scalar field is a scalar for each point in space. So that might be something like the density of a material or the temperature on a weather map. We've also met vector fields. They might be things like wind velocity on a weather map or the electric field or something like that. We've also met tensor fields. Something like a polarizability for a material is actually a function of where you are in the material. And so therefore you don't just have a tensor, you actually have a tensor for each point in space. Now supposing we have a scalar field on space-time. So there's our scalar field. It's actually a function of space-time. So I could write it like this, which is sort of code for x0, x1, x2, and x3. We know that that is a tensor field because a scalar is a trivial example of a tensor. What about the derivative of it? Supposing I was to take the derivative of this with respect to the coordinates. Now this derivative, by the way, we often use shorthand notation because remember physicists can get quite lazy when they have to write the same symbols large numbers of times, so we often write that like that. Another equivalent notation for that kind of derivative is in fact just a comma. So how does that transform? Let's have a look. Well, if I've got something I'm taking the derivative with respect to one set of coordinates, and I instead want to take the derivative with respect to a different set of coordinates, then in fact I know how to do that. That's just the chain rule. It's a multivariable function, so this is the multivariable version of the chain rule where we're summing over this parameter nu, which is the set of old coordinates. Now we know what this is, or more specifically we've given it a particular notation. And so this thing here is actually transforming exactly like a covector does. So this notation where we put a comma at the bottom and a nu down there is kind of suggestive that if you take the derivative of a scalar field, you end up with a covector field. And in fact you do. We've found that it transforms exactly like a covector field. What about derivatives of higher order tensors? So supposing I have a vector field, I'm going to take the derivative of that. How does that transform? Well, now we have not just new coordinates for our derivative, we also have new coordinates for our vector field. But we know how tensors transform, so we know how to do that. And we know the chain rule, so we can do this. And we get the extra term distributed over here of the p's. Looking good so far. We know how to do this derivative. It's just a product rule. And so you can see we almost made it. If this term here was 0, then this is exactly how the tensor field should transform if in fact this is a vector and covector tensor. So we've got two indices, one up and one down, and so we should have it transforming just like as though we'd added a covector element to this tensor. However, this term here is not necessarily 0. However, for a lot of the transformations where we're just going from one inertial reference frame to another inertial reference frame and we're staying in Cartesian coordinates, then in fact, this is, remember, just our change of coordinates, our derivatives of our old coordinates with respect to our new coordinates. So these things ought actually to be linear. So for example, in the Lorentz transforms, then this matrix here is exactly this matrix of derivatives, and you can see it doesn't contain any x, y's, z's, or t's in it. And so this derivative would be 0 for the Lorentz transforms. It would also be 0 for rotations and other things that transfer us between Cartesian coordinate-based inertial reference frames and other Cartesian coordinate-based inertial reference frames. Now in special relativity, we're only interested in those cases. We're only interested in transforming between inertial reference frames because those are the frames in which our laws of physics have to stay constant. So this motivates introducing Lorentz tensors. And derivatives of Lorentz tensor fields are in fact Lorentz tensor fields. Let's do a quick example to help practice the maths for these tensor fields. Okay, I want you to show that this equals this, where this thing here is constant and symmetric in the coordinates mu and nu, and this thing here is just an arbitrary vector field. All right, have a go at that cold and then come back.